and only Professor Bari. Please join us in giving a round of applause that he truly deserves. Please keep on clapping, guys. He truly deserves a round of applause. A very good afternoon to one and all present here. Louder, louder, guys. A very good afternoon to one and all present here. First of all, thank you for joining us here today for this very special occasion. Again, introducing ourselves, I, Antariksh Fukan from Department of Social Work.
And I, Shwarbani Borwa from the Department of Political Science.
Our anchors for today's journey.
And the moment we all have been waiting has finally arrived. Our esteemed guest speaker, Professor Bari, has joined already, and can we please have a huge round of applause for him once again.
Louder, guys. I request everyone to kindly take your seats, please. A very good afternoon to one and all present here. First of all, thank you for joining us here today for this very special occasion. Again, introducing ourselves, I, Antariksh Fukan from Department of Social Work.
And I, Shwarbani Borwa from the Department of Political Science.
Our anchors for today's journey.
And the moment we all have been waiting has finally arrived. Our esteemed guest speaker, Professor Bari, has joined already, and can we please have a huge round of applause for him once again.
Louder, guys.
As said by Albert Einstein, education is not merely the learning of facts, but the training of the mind to think. This quote beautifully encapsulates the essence of our gathering today. Good afternoon, everyone. Welcome to the University of Science and Technology, Meghalaya. It is with great enthusiasm that we stand before you today to celebrate knowledge, innovation, and inspiration.
कहते हैं कि उम्र सिर्फ एक संख्या है और आज हम इस कहावत को सच्चाई में बदलते हुए देखेंगे.
Today's event is really special as we have the distinct honor of inviting a remarkable individual who has captured the attention of the academic world and beyond. This special guest is none other than the youngest professor in the world, Suborno Isaac Bari.
As many of you know, Professor Bari is often referred to as the Einstein of our generation. Please, can we have a huge round of applause on that?
Yes.
Einstein of our generation. Despite his young age, his contributions to the field of science are truly extraordinary. His journey is a testament to the incredible power of curiosity, perseverance, and the pursuit of knowledge.
Before we dive into today's proceedings, let us take a moment to appreciate the impact of Professor Bari, who has made not only in advancing scientific thought, but also in inspiring young minds across the globe to dream big and aim high. At just 11 years old, Professor Isaac Bari has been recognized as the world's youngest professor, a prodigy who has captured the attention of the global academic community with his remarkable intellect and passion for science.
As said by Malala Yousafzai, let us pick up our books and our pens. They are one of the most powerful weapons. Professor Bari's journey into the world of academia began at an incredibly young age when he started solving complex mathematical and scientific problems that left even seasoned scholars in awe. His profound understanding of subjects like physics, chemistry, and mathematics has earned him recognition and accolades from prestigious institutions worldwide.
But Professor Isaac Bari is not just a scientific genius. He is also a strong advocate for education and innovation. He believes in the power of curiosity and is deeply committed to inspiring young students to pursue their interest in STEM fields. His mission is to make science accessible and enjoyable for everyone, regardless of their age and background. But before we proceed, let us take a moment to acknowledge the presence of our distinguished guests and dignitaries. Your presence here today adds immense value to this occasion.
And now, may I kindly request our Honorable Chancellor, Sir, Vice Chancellor Sir, an Honorable Pro-Vice Chancellor Sir and Advisor Sir to present Professor Isaac Bari with a token of love and appreciation from the USTM family and a goodie bag comprising of organic products from the entire Northeast. Come on guys, louder!
We are also privileged to have with us the proud father of Professor Suborno Isaac Bari, Mr. Rashidul Bari, teacher of Brooklyn Tech, USA, New York, and Mr. Pranesh Devnath, State Representative of Northeast India, Vyomika Space Academy, and India Coordinator for Professor Suborno Isaac Bari. And now I would like to request the proud father of Isaac Bari, Mr. Rashidul Bari, to come over the dais for the felicitation. And now I would like to request Mr. Pranesh Devnath to come over the dais for the felicitation program.
Mr. Devnath.
Mr. Devnath, can you please come over the dais? Mr. Devnath, we request you to come over the dais for the felicitation.
Mr. Devnath, can we have a huge round of applause for Mr. Devnath?
State Representative of Northeast India, Vyomika Science Space Academy, and India Coordinator for Professor Suborno Isaac Bari. Can we please have a huge round of applause again?
Today we are truly honored to have Professor Isaac Bari with us to share his insights and experiences.
Professor Bari, we are all eager to hear your thoughts. The stage is all yours now. Can we please have a huge round of applause?
So can we hear it for Professor Suborno Bari once again? A big round of applause. Professor Suborno Bari, the stage is all yours.
Thank you very much, ma'am. It's my honor to be here today. Greetings, namaste, and assalamu alaikum to the entirety of the University of Science and Technology, Meghalaya. It is my honor to be here today. Now, today, I want to keep this lecture short, as always, because you may have seen the itinerary. This is supposed to be a 1 hour or so long lecture, but what I really want to do is keep it short, because the best speeches are the ones that keep your viewers' attention for the duration of the speech. And of course, I can't do that if it's 1 hour. Half of you are going to take out your phones by then and scroll on some random social media app. So, why am I here today, and why did I specifically choose to talk about the impact of early STEM education? Well, it should be pretty apparent that I was given some early STEM education myself. And I think that early STEM education, I've said it 3 times by now, but the impact of educating your kids at a young age about STEM might be one of the biggest things that has ever been seen. But people don't really use it that much, use that opportunity. The thing is, everybody gets exposed to STEM technically at a young age. At 3 or 4 years old, you start counting, you start adding, you start subtracting, but you have so much potential to help your kids understand before then. Now, of course, I'm not talking about making your kid do calculus. I'm not talking about your kid doing calculus at the age of 2, but I think that early exposure, now the people in the back can't hear me. So early exposure to science, technology, math, and engineering is one of the most important things any child can have. And why is that? As we become older and older and older, suddenly more and more people start getting this fixed mindset. They believe that either they are right about everything, or when they don't know, their teacher is right about everything. One time, Yesterday, in fact, I was giving a public lecture quite like this one, and right after, a question and answer session at the ERD Foundation Guwahati. And we were having some high school students come on and ask me a few questions. So, one of them asked me a very profound question about set theory. If you have a set of every single set, does it contain itself? Is it even a set? And I think, personally, the answer is no. Why? Because something that contains multiple sets is not a set itself. That would create multiple paradoxes. It is what we call a collection of sets, and a collection of open sets, a collection of closed sets, whatever you want to call it. It's a collection of sets, not a set containing other sets. All a set can contain are numbers. Of course, that's in the sense of real and complex analysis, not anything else. And this student refused to think any differently. This student haggled with me for half an hour. While all the other students, I answered their question for 5 minutes, and then they went away. This student told me, "But I don't believe you, sir. Why do we even need the concept of a collection? Cannot a set be an element of another set?" And sometimes it's good to be hard to convince. It shows that you're not just taking what anybody says for granted. You actually want to see what's in there for yourself. But then I explained to him, if you have a set that contains other sets, what if that set contains itself? Wouldn't that create multiple paradoxes? What would be the length of the set? What would be a subset of that set? So things would be very complicated if we did not simply call this object something other than a set, something that we call a collection of sets. But he refused to believe me. And at one point, he even cited a definition that a set is a generalized collection. And I asked him, well, I just used the word collection, but a collection of what? What is a set? What is it a collection of? And I mean, most of you would fill in the blank as numbers, whether it's natural numbers or rational numbers or real numbers or complex numbers, but he didn't answer my question. He just said it's a generalized collection. A collection of what? Shapes, fruits, words? It doesn't really tell you anything. So, what I told him was, I mean, this isn't how a set works. A set can only contain these amounts of numbers and nothing more. If we have multiple sets, then if we have an object that contains multiple sets, we call that a collection. And so he said, okay, thank you so much, sir. But the look in his eyes told me he wasn't satisfied at all. So, I mean, these people have fixed mindsets. Why? Not because they are actually listening to anything you say, not because they actually want to find the truth out behind anything, but because they can't be convinced that they're wrong. They can't be convinced to think from a different perspective. And of course, if any of you are in political science, for example, or law, you will have probably seen this all the time. But in terms of math and science, this is a very pertinent issue as well. And this is why so many people drop out of math and science majors as they go on. When it comes to your high school, all you have to do is pass tests and get good grades. When it comes to your bachelor's degree, your BSc, you need slightly more creativity. You need to understand how to conduct experiments. You need to conduct some research for yourself if you want to get into a good graduate school, etc. It takes a little bit more effort. But when it comes to your PhD in any STEM field, the difference of that is, in your bachelor's degree in your high school, you're learning stuff that other people have already created. But when you talk about a PhD, you're asking someone to create knowledge that has never been found before. And oh boy, is that incredibly hard if you have a fixed mindset. If you can't think about anything, if you can't stand to think of something from a different point of view or connect two things, then, I mean, you're never going to get anywhere. You're never going to get your PhD. And that's why almost half of people, at least in the US, the data is, about half of people drop out between their high school and their bachelor's degree when it comes to math and science. And only about 30 or 40% of people who complete a bachelor's degree in math, in physics, math and science, of course, only go on to get their PhD, which is a very unfortunate thing. Why? Because, I mean, so many people say these courses, differential calculus, integral calculus, multivariable calculus, they weed out the people who aren't worthy. But who isn't worthy of math? Who deserves to be weeded out? Who doesn't deserve to actually be part of the future of how our world works? I mean, nobody. Nobody should be excluded from math and science. So why do we say these classes weed out so many people? And when we say that, why are we correct? Why do so many people drop out of STEM once they get through the ring of calculus classes? Or even earlier, most people can't drop out of STEM when they're in middle school or high school, but they completely lose interest when it comes to variables and such. Many people I hear, at least in the US, say math got much worse when letters started coming in. And it's so confusing to them. So why do these classes weed out so many people? Well, here's my understanding of it. Math and science has become so robotic over the ages. Not math and science itself, in terms of the front line of discovery, but math and science education and Common Core. Not just in the US, but everywhere. Math and science has become the same formulaic approach repeated over and over with different problems when it comes to school. And of course, a lot of problems, textbook problems in India have a bit more steps than those in the US, but still, they're nowhere close to anything you would actually find in the real world, which not only requires lots of formulas and creativity, not just a lot of formulas, but also a lot of understanding and a lot of creative thinking, which is not what we see nowadays. And that's a very unfortunate thing. Of course, I hear that on the IIT JEE and on the JEE Advanced and the NEET, you don't really get that many formula sheets. I believe you don't even get a formula sheet at all for the JEE Advanced. So, in fact, I was asked a question from somebody's NEET textbook for one of the schools I went to, and it was just a formula question. It was just memorization. It was asking, what is the induced magnetic field around the current carrying wire? And obviously, everyone who's a physics major knows the answer to that, mu naught I over 2 pi r. But it's just a memorization question. There's no actual substance to it. There's no actual understanding. And I doubt that anyone who's teaching this actually bothers to explain why this is in class. They just say, here's the formula, move on. And the worst thing is, in the US, you get these formula sheets. So they have to come up with more creative questions than, what is the formula for this? But in these questions, no. All you're asked to do is memorize. There's no real creative thinking behind them. And the most creative problem I received that day, when they were asking me questions from the physics section of the NEET, was a problem that used not one formula, but two, the continuity principle and Bernoulli's law. Two formulas. And they were just applied one after the other. No algebraic manipulation, no little twists or turns, absolutely nothing. And that's very, very unfortunate for us. We should be learning how to creatively think, how to actually arrange these mathematical and scientific formulas. But instead, we're learning what the scientific and mathematical formulas are, and not how to use them, how to understand them, or even where they come from. That is the most unfortunate thing about STEM education right now. But how do we change it? It's not like we can reteach every single teacher or replace every single teacher. That would be even worse. We simply don't have the infrastructure or the practicality for that. What we need is not to completely overhaul teaching. Over time, I'm sure that will work. But we need to find other resources on our own. So I think one of the most impactful things parents can do for their children to stop this kind of phenomenon happening, to stop them from dropping out of school, STEM as they become older because it's getting too abstract for them. The most parents can do and schools can do is teach STEM early. And of course, every school teaches science or math in some way once you're 3 or older. But what I mean is not teaching via the standard curriculum. What I mean is introducing these abstract concepts in a way that actually feels down to earth with them. I once asked one of my classmates who was failing in algebra, why don't you understand algebra? And this was at the beginning of the high school year, by the way. And he said, well, I just don't understand. In one equation, x is 2, and in the other, x is 3. How did it change values between those two? And don't laugh at him because, I mean, it's only natural for him to ask. I thought these variables were specific names for numbers. Now suddenly they're changing in between. I thought that x always meant 2. Why does it mean 3 now? And so many people are confused about this as well as other concepts in algebra and trigonometry and basic high school math. They don't understand that x isn't a name for specifically one number. They don't understand that x is just a mystery name. It's a general name we apply to a number that we don't know. That's why we don't just use the number in the first place. So, these people don't understand how abstract math is. And how do we fix that? Not by introducing a whole new math curriculum that teachers don't have plans prepared for, but rather by introducing these concepts earlier, not to spend extra time on these small concepts, time that you don't have because you have to prepare for a bunch of exams that come at the end of the year. Instead, we have to spend time introducing these abstract concepts earlier. And of course, you may know, if you study the history of math and science, that people have tried this, at least as far as I know. It was tried in the US in the 1960s before, a curriculum that they called New Math, where they taught more abstract concepts on a simpler level. They taught set theory and group theory to 3rd and 4th graders. But the problem was, not only did they prioritize this new abstract math over things that students were supposed to be learning, like addition, multiplication, fractions, percentages, and so on and so forth. Not only did they prioritize the abstract math over the practical math, but even worse, most parents and even some teachers didn't understand the material that they were supposed to be teaching, which leaves me scratching my head because these people are supposed to have a bachelor's degree in math. But what I'm thinking is, why don't we don't have the infrastructure to make a change so quickly? And that's what you're probably thinking as well. And after only 5 years, a book was published named Why Johnny Can't Add, The Failure of New Math, and that quickly enlightened the public to what was going on, and the program was shut down. So I think this time something in that vein can work. But we don't need to make that switch immediately. That'll just harm people in the same way that new math did 60 years ago. Instead, what we have to do is we have to actually prepare not only our teachers, but the parents around us to help their children and their students with mathematics. We have to actually prepare these lesson plans a few years in advance. And most of all, if your teachers aren't changing, the only thing you could do is ask the one other resource you have at home, your parents. So your parents are the ones who are looking out for you. They're supposed to provide for you. And that doesn't just come for food and shelter and bills and stuff. That also comes for your education, your understanding. They're supposed to provide to you the things that you can't understand yourself. And so, for those who are parents in this room, I would like to ask you, please, learn at least a little bit of math, like my dad did. He was going for a degree in law, and he eventually thought he would end up going into law. But then, once he had his first child, my older brother, and then especially once he had his second child, me, he thought, I need to help these kids with math and science. I need to inspire them in some way that will leave a mark on them. And so he decided to get a math degree. And even though he failed 5 times on end, he failed Calculus 1 5 times in a row, he managed to get through it and get his bachelor's degree in math, along with 4 other bachelor's degrees. So I think we need a round of applause for the man who's currently hiding behind the whiteboard. But of course, we're not done. Okay, you could go back behind the whiteboard now. Okay, so I'm not done. I think that the parents in this room today have to follow the example of my dad. They have to actually go out there and not do something as extreme as re-earn a BSc in math. I think there are actually age restrictions on that kind of thing in India. But at least learn a little bit of math. Help out your children. And don't just repeat textbook definitions to them. They already get that bullcrap in class, and they still don't understand it. You're supposed to actually intuitively explain it to them on a deeper level. And of course, they're children, 13 or 14 or 15 years old. They won't understand everything perfectly well. But I hope, hopefully you who is 35 or 40 or 45 or 50 or somebody somewhere in that range. Why are the lights going out? You should be able to understand these concepts on an intuitive level and explain it to these children who are in need of help. So that's just my advice to all of the parents out there. And to the students here, not only the students who are still in middle and high school, junior high school and high school, but also the students who are currently in college. I'm sure there are some things you don't understand, not just for the people who are in math and science, or STEM in general, but also people who are in other fields, like commerce, economics, law, pharmacy, and other medical subjects, biology, chemistry. Oh wait, no, chemistry is STEM. Anything else in that field. I think that people need to understand that they're not alone and that textbook jargon and teachers who ramble on for the entirety of the semester are not the only resources that you're stuck to. So I think that although there are resources you could cling to when you're older, the biggest thing that can help you is the impact of STEM education early on. Giving your kids that education is enough to inspire them. So there are so many examples of this. But I think that just this early exposure, if they get inspired from it, they'll be able to do math for the rest of their lives. But as they grow older, this view is slowly cemented into them that math is just this formulaic slop, that it's not anything actually practical for your life. And that is the exact kind of mindset that you can avoid by teaching your kids early. So I would like to encourage you all, please, if you're planning to have a kid, which I'm sure is very few of you, or if you already have a kid who's very young, like 9 or 8 or 9 or 10, you have to teach them math now, because as they grow older, they will learn to stop asking questions. They will learn to stop being inquisitive. They will learn to not like math and physics anymore, or STEM in general, because that field is all about asking questions and being inquisitive. And they will simply learn that all they have to do is memorize the formulas and listen to their teacher and get good grades on their exams. So I implore you to do this now before it's too late. Thank you.
Hello again. Let us now begin with the interactive session. There are some students from our department and our university, and the concerned students, I'll request everybody to please stand up, and Professor Isaac Bari will answer you guys. So there are a couple of questions from the mathematics department. The first question is from Alvoda Marvin, PG, third semester. When an object approaches the speed of light, its mass becomes infinite. Why?
Okay, so first of all, you guys are supposed to clap for them. What's their name?
I request Alvoda Marvin from PG third semester to please come over the dais and raise your questions.
Is there an Alvedana Marvin?
I would also like to request Imon Mondal from PG third semester from the Department of Mathematics to come over the dais and interact with sir.
I know about you, but these sound more like physics questions than math questions.
Mr. Arnab Datta, BSc Physics, first semester. Bedanga Basumatari Bora, BS Physics, first semester. Ms. Somreen Hussain, Physics, third semester. Ms. Vijumsi Chitom, BSc Physics, fifth semester. Shainaz Akhtar, MSc Physics, third semester. Mahmood Ajmal, MSc Physics, third semester. Mehbooba Rahman, MSc Physics, third semester. I request everybody to come here and interact with Professor Bari.
We also have few registered participants from the school of Rampur Chalpathar Jatiya Vidyalaya. So the name of the student is Ajibul Haq. We also have students from Little Angel School, Yusuf Mohammed and Yasmin Nahar, to come over the dais and interact with sir.
And the students from Maths Department, Alvoda Marmin, PG third semester, Imon Mondal, PG third semester. Request everyone to please come to the dais.
We would start with the Department of Mathematics. We would like to have Alvadona Merwin from PG third semester.
Oh, does PG mean physics graduate?
Postgraduate.
Oh,
Postgraduate.
okay.
My name is Arnab Datta. Welcome to USTM, sir.
Thank you.
So my question is, what is the
Not yet.
significance? My question is, what is the significance of the speed of light being constant in all inertial frames of reference, and how this lead to the concept of time dilation?
Okay, so essentially, this is a very good question. So the speed of light being constant in all reference frames, of course, comes from the 4 Maxwell equations. And why is it significant? That's an absolutely wonderful question. So normally, you already know, obviously, since you're in your 3rd year of postgrad, that if we just have a regular Euclidean point in space, so what is the only thing that is invariant in R3, no matter what reference frame you're in? The only thing that's invariant is distance. Velocity can change, acceleration can change, position can change. But the only thing that doesn't change is distance, no matter if you rotate your reference frame or you translate your reference frame. So distance is invariant in R3. But the thing is, this changes when you introduce the fact that the speed of light has to be constant. Now, instead of our constant being something like this, like dl squared is equal to dx squared plus dy squared plus dz squared, instead of this being our space-time interval, now, to keep the speed of light constant, we have to add an additional component. And, of course, this is what leads to time dilation. Now, I'll give a Neil deGrasse Tyson way of explaining time dilation, and I'll give an actual mathematical way of explaining time dilation. So, of course, the fact that the speed of light is constant in all reference frames, the velocity, or speed, just is equal to the distance covered over time. But distance is invariant, but distance is invariant, and it seemingly so is time in Newtonian. So, a velocity is supposed to change to accommodate all reference. Okay, I'm going to explain it a little bit better. So, let's say you're in a car traveling at 30 kilometers per hour. I don't know what you guys use over here. And then somebody is walking by at 3 kilometers per hour. So then, and let's say you guys are walking in the same direction. Then, in the car, you will perceive yourself as traveling at 0 kph, and that guy is traveling backwards, 27 kph. And I know you might think that sounds like nonsense, but I mean, look on the outside of your car or your bus or wherever whatever you use to get here. I mean, if you see any still objects, you will perceive them as moving backwards away from your direction of motion. So, however, this is not the case with light. If you have a guy running over here at 3 kph, totally fine. But now, let's say we have light. Light is going to be moving here at 3 times 10 to the 8 meters per second. Now, converting that into kilometers per hour, first we have 3 times 10 to the 5 kilometers per second, and then all we have to do is convert this, multiply this by 3,600, so that we get hours, and then all we get is 10,800 times 10 to the 5, or 1.08 times 10 to the 9 kph. So it's safe to say this guy is outspeeding you by a little bit. But the fact of the matter is, no matter if you're traveling at 30 kph, or 300, or 3,000, or 30,000, no matter what, you'll see this ray of light is traveling at the exact same rate. But this conflicts with our definition of velocity. Velocity is supposed to be relative. So, in order for that to change, distance has to be variable and time has to be variable, which is exactly the concept of Lorentz transformations. And normal transformations in Euclidean space, this the distance between two objects is held constant. Obviously, this is just the Pythagorean formula. But here, it's not the distance that is being held constant. This is what we call the space-time interval. So, essentially, transformations in relativistic space are supposed to make this stay constant. And so, transformations that keep this constant are known as Lorentz transformations. And long story short, you can essentially calculate what these Lorentz transformations are, their general form, and what it will give you is a proportionality constant, gamma, times whatever vector you originally had. Okay, well, let me write this in a better way. The Lorentz transform is often written as a capital lambda. So what will happen is you'll often have capital lambda times any vector you have is going to be equal to the same exact vector times a certain constant called gamma. And this constant, which you can calculate, is specifically equal to 1 over 1 minus v squared over c squared. And this is essentially how you calculate time dilation. So, what I believe is that the time that others observe is going to be the time in your reference frame, also known as the proper time, divided by gamma. So essentially, time dilation occurs because the velocity of light has to stay constant in all reference frames, but this contradicts our normal sense of velocity in Newtonian mechanics. So to change velocity, which now has to be invariant, to keep velocity the same, we now have to change distance and time, which were originally invariant. And so this results in length contraction and time dilation. So essentially, the fact that the speed of light has to be the same in all reference frames results in all other physical quantities being stretched and squeezed by some certain Lorentz transform to account for the fact that the speed of light has to be the same. So that's the significance of the speed of light being constant. Thank you. Okay. There we go. That's how.
Right hand.
Oh, got it. Okay, take your question back.
Next
Great.
question. For the next question, please come and introduce yourself. Which department? Come.
Before we begin, myself, Badanga, it's a pleasure to meet you.
Thank you.
And I'm from physics department. That's nothing to concern with. Well, my question is all about quantum computers.
Oh.
So I recently read an article about quantum researchers recently announced that the first step towards building a more reliable quantum computer, said to measure without losing information. Is this possible in today's time with quantum errors and trickiness? Just have a look at it.
Okay.
Just have a look at it. There's still a trickiness in quantum computers. There are errors, 1 in a billion qubits, most probably due to the temperature, vibrations in the room.
Yes. Okay. How do you propose a brilliant... Okay. I am not a quantum scientist, so I don't really know how to keep the reliability of qubits stable. But, I mean, what I would say from the very little that I know about quantum mechanics, you know definitely more than me, given that you're...
I don't think I know more than you. I'm sure you know more than me.
Given you're in your third year of BS... Oh, wait, no. You're in your first semester? Okay, so let's see. I misread that, sorry. Okay, so... what I would say is that I can't propose anything, obviously, but I think that it wouldn't be very possible right now because to keep these qubits perfectly stable, especially such a large amount of them as 200, you'd have to keep every single possible fluctuation in the room stable. That's just not something that we have the ability to do on such a large scale as 200. Maybe we could do it for 1 or a dozen or so, but for 200 or 2,000, it simply seems impossible to keep fluctuation of temperature, pressure, and all these other things, all these quantum computing components completely stable. And so, of course, you need qubits on the order of thousands or 10,000s to do useful work that can outpace a classical computer. So, I think that losing information is going to be an inevitability for the next few years until we find some way to reduce these fluctuations. I'm sure there are some ways to do so. In the same way that we can damp sound and damp movement, I'm sure we can damp the vibrations of temperature in a very similar way, but I can't propose anything right now that's very specific.
Well, even if that's the matter, I have another thing to ask. For imagine there's a quantum entanglement between two particles, one rotating clockwise and another, if one rotates clockwise and the another rotates anti-clockwise, even if they are light years apart. So how about we choose one clockwise rotation as 1 and the anti-clockwise as 0. With that, we can exchange informations like a wormhole from one place to another place using quantum computers. What do you think about this idea?
Okay, this is great. This is a great idea, but here's what I personally think about it. So one way, the best way that I've heard to explain this quantum entanglement is to say that you have two shoe boxes across the galaxy. You know one of them contains the left shoe and the other contains the right shoe. So once you open one, you immediately know what's in the contents of the other. You open one and you get the left shoe, you know the other one has the right shoe. So you open one box and you get a clockwise spinning particle, you know the other has an anti-clockwise spinning particle. But the problem is, you can't actually communicate that you know this fact without using, for example, a radio message which travels at the same speed as light. So of course, you yourself know this information, but you can't actually communicate it to anybody else without using the normal speed of communication. So, I mean, it's kind of useful, but I wouldn't say it's very useful.
I mean, in future it might be possible. In future, near future, not now.
Perhaps, but I feel that even if you can actually see, the thing is, with entanglement, you get one and then you see the other. But the thing is, first you have to communicate that you see one to the people who can't see either of them. Okay, here's one way to put it. Let's say you had 0 and 1, like you said, the clockwise and counterclockwise. So of course, once you see the one that says 0, the one that's spinning clockwise, you know the other one is going to be 1. It's going to be spinning counterclockwise. But the thing you actually have to communicate is that either you saw 0 or that the other one is going to be equal to 1. And of course, that's a very small amount of information. It's smaller than the usual one that you need to give, that one of them is 0 and one of them is 1. So it reduces the amount of information we have to use, which is definitely useful for memory purposes. But in terms of making communication faster, you still have to communicate the same kind of data. No matter how much there is, it usually travels at about the same rate. So I would say that while it is probably going to be useful for conserving memory, I don't see it being useful for making it faster.
Thank you very much, Professor Isaac.
I think we can meet again.
Yeah, sure.
We are now
Let the other person
having a serious discussions,
I'll let the other person
question
go.
answer session with Professor Isaac Bari. I'll request all the students, those who are participating in the question answer sessions, you are most welcome. But please come with a one student, one question. And the question should be from the physics or mathematics. Calculations are appreciable. Otherwise, you don't come with a third law of attraction, third law of motions. I got so many questions. So, not like that. You challenge the Professor Isaac Bari. He's away from University of New York. From India. He's from USA.
No, don't
Okay,
worry.
challenge him with mathematics.
Don't worry.
Tough questions. Throw him.
Okay. Don't
Okay.
worry, I'm not
Please
that
come.
restrictive.
Next mathematics questions, yeah.
Don't worry, I'm not that restrictive. But,
Alvadona Marvin from the Department of Mathematics, PG, third semester.
Okay, 1 second. I'm not that restrictive with questions, don't worry. The only reason Mr. Demnath is saying this is because last time someone asked me, do blind people see in their dreams? So, no, we're not having questions like that again.
Okay. Hi, sir.
Thank you. Hello. Good afternoon.
Good afternoon. My name is Alvadona Marwain, and I'm from PG third semester, Mathematics Department. So my question today is, when an object approaches to the speed of light, its mass become infinite. So can you please tell me why?
Of course. So, in the same fashion that I just explained, we already know that, of course, because of the Lorentz transformation, so the Lorentz transformation actually has to follow some very specific rules, you see. So the space-time interval, which is what we keep constant in general relativity, this thing has to stay constant, is equal to this. And of course, c here means the speed of light, t is time, x, y, and z are the three space coordinates. And of course, this is just a small variation from regular Euclidean space. So then, what we could do is we can use what we call the Minkowski metric, which looks like this, to encode this information in a better format. So how does this have anything to do with that, of course? Well, it's very simple. All this is just you take dt, dx, dy, dz, and then you multiply the metric in the middle, and then you get the row vector dt, dx, dy, dz. And of course, you can do the maths by yourself, but all this does is simplify to this form. Oh, crap. Okay, so what we're actually going to do is use Gaussian coefficients, which is going to remove the speed of light or set it to 1 instead so that we can work in peace. And so now, all that's going to happen here is that this is just going to have to be equal to the regular metric weight. Oh yeah, so all that's going to happen here is that this has to be equal to, of course, just this space-time interval right over here, which means something very special, right? So what I'm going to do is I'm actually going to write this as this, which is an abbreviation for all of these, times the metric, which looks like this, times this, which is just a row vector instead. So that means it's the transpose. And this has to stay constant, right? So that means that once we apply the Lorentz transformation, just like so, let me just rewrite this. Why do I hear people giggling? So, if we reapply the Lorentz transformation, what we're going to get is something like this. This is in the wrong order. Of course, once you take the transpose of these, it's going to be in reversed order, which gives us something like this. And this has to be equal to the normal format, because of course, everything has to be conserved, which leaves us with the special equation that this, the Lorentz transform times the Minkowski metric times the Lorentz transpose has to be equal to this. And of course, this is a very special class of matrices. And of course, all we do is, in two-dimensional coordinates at least, we set this to just be equal to some matrix with components A, B, D, F, for example, which means the transpose is going to be A, B, A, D, B, F. And of course, then we just solve for it using the regular Minkowski metric. Now in the 4 dimensions that real relativity uses gets a lot more complicated, so we usually just use computers, but this is a nice exemplary example. What did I just say? So then it turns out that what we get is going to be, end up being something in this format. It's going to be some constant, 0, 0, if I remember correctly. And then, oh wait, no, this is the identity. It's going to end up being something like this. And then, over here, we're going to get a proportionality constant, beta. Beta squared, actually, I believe. But whatever it is doesn't matter. The fact is, beta is going to be very important because it's equal to the square root of 1 minus v over c squared. And so, what we call the gamma factor is just 1 over this. So then, this gamma factor is responsible for dilating every single quantity. So that includes mass. Mass itself might seem like a scalar, but it itself has to be dilated too by this, because this is actually sort of dilating not mass in specific, but what we call the stress energy tensor, the mass energy tensor, this, which encodes all of the mass and energy in a 4x4 format, which essentially has a lot to do with the Maxwell's equations for electromagnetism. So, the point is, we multiply this proportionality constant by this, which is essentially what mass is. And so, that means that, in essence, we're multiplying mass by the regular mass times the speed of light. So the rest mass times, not the speed of light, oh my goodness, the gamma factor, which is this. And of course, as you said, why does mass approach infinity as velocity approaches c? Sorry, I think I'm dying of heat stroke. So, why is this true? Well, of course, if you look closely, you'll observe that beta is going to approach 0 as v approaches c, because, this is 1 minus v over c squared, so of course, if you plug in c, this is just going to give you 0, because c over c squared is going to be 1, you see it. So, since gamma is 1 over beta, then as v approaches c, gamma is going to approach infinity, because of course, the denominator is getting smaller while the numerator stays the same, which means it's going to go up and up and up and approach infinity. So that's essentially a short answer for why mass approaches infinity. Thank you.
I should big round of applause, I think. This is a tough question, not for the Professor Bari only. I also think the students that who has raised such a question, beautiful questions, in front of all the parents, students sitting here is very appreciable. Yeah, now we have a question from the little kids. So go there and read out the question.
We have a child prodigy, Ronak Tanveer from class 1 Little Flower School. Tanveer, please ask your question.
Go there, I am there.
Oh, thank you. How old are you? How old is he? Why does he have a water bottle around his? Okay, what's the question?
My question is my question.
Guys,
Why is electric current considered a fundamental quantity?
Why is electric current is considered as fundamental quantity?
wow, that's a hard question.
Because
What?
because there is noted that as charge per unit time. There are two quantity is involved in it.
Okay, that's a very good question. So essentially, what he's saying is that amps, or essentially current in general, uses the units coulombs per second, right? Or amps. So, this is using something that is already a fundamental unit itself. So, why isn't this considered a derived unit? And I think that's a very good question. And the reason is, I think that charge should be charge should be the SI unit, but of course, the international standards have decided that coulombs themselves are not a derived quantity. Coulombs are completely original. And of course, there's been a big debate in the SI standard, in the standard international community about whether charge or current should be a standardized unit, but most people have said current. Now, I don't know why, because of course he raises a good point about this seemingly being a derived unit, so I'm going to have to think it over. this is the first question that I don't think I can answer.
Thank you very much. We are running out of time, so next question, please.
Next, we have Yasmin Nahar from Little Angel School. Please come over, please come over. Her question is when we can use conservation of momentum in daily life, please.
Myself Yasmin Nahar from Little Angel School. I am from class 9 and my question is when we can use conservation of momentum in daily life.
So the truth is, physics, especially conservation of momentum, is absolutely useless and my life is a lie. Okay, so conservation of momentum in terms of daily life, well, essentially conservation of momentum is applied in a lot of different ways. So for example, if you're a good 8-ball player or billiard ball player, I don't know what they call it, the pool, the game where you take a stick and whack the balls around into holes. That is the most glaring example of conservation of momentum, as once one ball hits another ball, this ball nearly completely stops, or it heads in another direction due to conservation of momentum, and the other one heads in the direction it was originally going. So this is the biggest example of conservation of momentum that you can find in your daily life. But of course, there are a lot of others. For example, there's a very big reason that you don't want to crash a car. Why? Because of conservation of momentum. The car is going to stop moving as soon as it hits the tree, but you won't stop moving. So you're going to fly right through the windshield and hit the tree in the face. So this is exactly why you don't want to crash a car. And in the same vein, you don't want to press both brakes on a bicycle at once, because you're going to keep moving, but the bike isn't. So your wheelie is going to go right into the bike, which is not a very good situation. So there are lots of places where you can apply conservation of momentum, and it's a very intuitive concept actually. And one more thing where you can apply conservation of momentum is airplanes. Now, lots of you may have wondered, especially if you're little kids, well, why don't airplanes just launch, stay in the air, and then wait for wherever they're going to rotate under them so that they can fly back down? And the reason is actually conservation of angular momentum, which is basically the same thing as conservation of momentum. And so, why is that? Well, the reason is, technically, you could do this, but it would cost way too much energy. It would cost so much more energy than using the angular momentum of the Earth to take off and actually go to your destination. Instead of that, what people are proposing you do is fly up into the air and exert a massive force this way to prevent the conservation of angular momentum from working. And of course, this also goes for rockets and so many more things. So in daily life, there are a few uses that you can already see that come from intuition, but if you actually go into a job where this is needed, like engineering, you'll see a lot more uses. So thank you.
Next, Imon Mondal, PG 3rd semester, Department of Mathematics.
So go there and ask the questions.
Yes, give me one moment. Is it like a long question? Or?
No, it's about something said earlier. At the very beginning of your speech, you said that there cannot exist a set which contains all the other sets. And then you said it's paradoxical. And feels like we have been wrong our entire life. And can you elaborate why it is paradoxical?
Okay, so here's what I'm going to say. So of course, as I said, an object that contains multiple sets is a collection. But why can't it just be another set? Well, by definition, sets are things that are just containing numbers, of course, within the context of a real and complex analysis. So, for example, the natural number is a set. The real numbers are a set. The set 1 plus 2i, comma 3 plus 4i is a set. And so on and so forth. But sets are not collections of other sets, because if they are, then what happens might be something like this. What's the length? What is, for example, the length of a finite set which contains something like this? Let's say a set contains itself minus the element 3, 1, 2, and 3. So then, what happens here? What's the length of this set? Well, you might say 4, right? Well, no, because, of course, this set itself has its own length. It's going to be S without 3, 1, and 2. So wait, 1, 2, 3, 4, 5, 6, 7? Well, wait a second. This is just, and this is going to keep repeating as long as you go on. And of course, this also runs into the paradox of having a set repeat elements, which it logically cannot do. So, how are all of these paradoxes fixed? Well, by defining a new object called a collection that contains sets. And a collection can't contain any numbers. That way, if we have a collection A, which is, say, a collection of the set S with S without 3, because you can't go with A without 3. A collection is just a collection of sets, not sets and numbers. So S without 3, and let's say, what else? T without 3 or something. Then, of course, this has a finite length, just 2. And you don't need to count what's inside these sets themselves, because a collection is simply a collection of sets, not a collection of numbers or elements within themselves. So, essentially, all I'm saying here is that this allows finite sets to be infinite in length and also repeats elements in sets, which is just a general no-no. So instead, what do we do to fix this? Well, we just define something new that separates sets from numbers. Essentially, we want to segregate sets from numbers so that no paradoxes are caused. Thank you.
Thank you, Professor Bari and Mandal, for asking a few beautiful questions. Next questions, please come forward.
Yusuf Mohammed, class 7 from Little Angel School.
What I really liked about that question is it showed he actually listened to the speech, which a lot of you probably didn't do.
Hello.
Hello.
My name is Yusuf Mohammed, and I am from Little Angel School, and I study in class 7th. My question is time traveling possible?
Okay, that's a great question. But unfortunately, I would have to say no. So of course, since you're in class 7, I don't want to get into general relativity too much. But essentially, what it says is that you've probably heard of the twin paradox by now. If you have your twin who is on Earth, you guys were born at the same time, so your age is the same. And then you go in a rocket at the speed of light and come back, your proper time, which is essentially the amount that you will have aged, is going to be less than your friend's proper time, which is essentially going to be the amount he has aged. So you have come back to a future version of your friend, essentially, what you might say. So you could travel your friend's proper time minus your proper time. And of course, this is because of the point of acceleration when you're going and then coming back. That's what causes this little change in proper time. But the thing is, we can't make it so that our proper time is less than the proper time of someone who's on Earth. And even if we could, well, we can't, but even if we could, that wouldn't be traveling into the future. That would just be essentially de-aging ourselves. We can't actually travel into the past because that would require us to, I believe, go faster than light, which is, of course, not possible by any object. So, if it is even possible at all, you can't exactly go into the past because it would require, wait a second, yeah, it would require a speed that is greater than light in this direction. So essentially, what I'm saying is that it's not possible because you'd have to go faster than the speed of light. But theoretically, if you could travel at some significant fraction of the speed of light, you could travel into the future, though of course you can't travel back to your past self. Thank you.
Thank you.
Okay, it's okay. I'll just grab this and, no, please. Okay. Yes.
Welcome to USTM, sir. My name is Lutfur Ali from Vision 50 and it is parent. My question is that if we see a galaxy from Earth we actually see the past of the galaxy because it's so many light years away from Earth. Is it possible to see the future of galaxy from Earth?
Let me see. Okay. Okay, that's a very good question. So the problem is, I'll just answer it directly, no it isn't. So here's the thing. The only reason we can see the past is because light takes time to travel. So, of course, maybe this is 4 light years away, which means the communication, the image that we see is actually going to be the light that hit us the light that started to come from it 4 years ago and just hit us now. So, it's not like something can be a negative amount of light years away. So it's not like we can have something that is -3 light years away, because of course negative distance isn't even a concept. Distance or displacement, no, not displacement, but distance in general always has to be positive, which means you essentially can't have something that's a negative distance away, which means there's no seeing into the future of a galaxy. Thank you.
Thank you. So this is the last and final question from Mehbooba Rahman, MSc third semester. Please come forward and ask the questions to Professor Isaac Bari. The final questions you are taking due to time constraints. We are not able to take the
Hello, sir.
all the questions.
My name is Mehbooba Rahman. I'm from physics department. We are very glad to have you here.
Thank you.
So my question is that, in the context of modern physics, how does the Big Bang theory explain the origin and evolution of the universe and the singularity? What are the key unresolved questions or challenges that the Big Bang theory faces in providing?
Okay, let me just see the full thing.
Yeah.
Okay, so that's a great question. So, okay, what I'm going to do is erase this. Essentially, the Big Bang theory is just a prediction that we use. Why? Because, as we can sense now, things are getting redshifted. The things in our galaxy are being redshifted. This is a blue marker, but you get the point. So, what that means is essentially the light coming from them is getting a higher frequency. And why is the frequency going up? Well, if you remember the Doppler effect, you'll remember that if something is coming towards you, then the sound it emits will have a lower pitch, and if it's going away, it'll have a higher pitch. And the same thing goes for light. So, as if something is coming farther away from us, then if we can't sense it in size, we can sense it in the color of the light waves that they send. So, via the quantity of redshift that we can see, or the quantity that we can see the universe is expanding away from us, we can sense that the universe has been expanding for a pretty long time. And so, that means that we can essentially trace back the conception of the universe to some singularity 14 or so billion years ago. And of course, we have evidence to support that it's this old, or something about that size. We have evidence to support it didn't just appear out of nowhere, because we have seen light from galaxies that are up to 13 billion light years away, so we can support that our universe is at least that old. But there are some challenges, I think, that it faces. First of all, what caused it? What matter interacted to create this initial explosion? That's the biggest question that the Big Bang theory poses. Because this question can be hand-waved off if we consider the universe to have, for example, existed for an infinite amount of time and just have recently started expanding. But if it just appeared out of nowhere, I mean, where did it come from? What was here before it started? Because of course, 13.7 billion years is a quantifiable amount of time. So where did this come from? And that's the very big question that the Big Bang theory poses. But aside from that, there aren't really very many big challenges that it faces. In fact, there's one very big thing that it explains that many people had thought of after a long time, light travels at a finite speed, but if the universe had been there for infinite time, or it was just stagnant, it wasn't expanding, light would have basically been everywhere by now. Why is it that when we look up at the night sky, our eyes aren't immediately singed because of all the light bouncing everywhere? Well, that's because the universe is still expanding. Most of the light that is emitted by objects in the universe isn't even going to reach us. Only about 6% of it is, because of the expansion of the universe. Of course, that's just assuming that it keeps expanding at its current rate and that the Big Bang Theory is true. But I think that personally it's the most credible theory that supports the creation of the universe. Thank you.
Thank you so much.
We are listening to Professor Suborno Isaac Bari, the renowned household names in the USA. He studies in the New York University in BS. Now he is a renowned name in USA. Every TV channels, big names are taking his interview. Yesterday also we got the NDTV 24/7 taken his interview online. Yesterday only, that I think it will be aired in view very soon. Professor Bari, thank you very much for taking giving us the very good time here in the Assam, in the USTM, University of Science and Technology. This is the biggest university, private university in Northeast India. Recently, NIRF has ranked him among the top 100 university in India. So, thank you very much for your valuable presence. I think your presence definitely will encourage the students community and the scholars community of this university. So, do you want to add anything to that?
For all your kind words. Is anyone hearing me? Okay. So, I really can't thank you enough for all of your hard work and all of your kind words. I was about to swap those two words, but I really would like to thank everybody who attended today. And since it's the day before Independence Day, and also since I'll be present at the university.
Call Chancellor, sir.
No, it's okay.
No, he's coming anyway.
Oh, really?
Yeah, next week.
Well, it's just been spoiled, so. Okay.
Thank you.
One more thing before I go. Since I will be here tomorrow for the celebration of India's 77th independence anniversary on August 15th here at the University of Science and Technology.
Further, I would like to call the proud father of Professor Suborno Isaac Bari, Rashidul Bari, to come over the dais and address the gathering.
You are worse than my student. Raise hand if you think mic is working. Good. I'm a teacher. Sometimes I behave like a teacher. So yeah. So let me start with Suborno's story. Suborno was born on April 9, 2012 in the United States. When Suborno was 6 months, he started talking. When Suborno was 1.5 years old, his mom took charge of teaching Suborno math.
Wait, 1 second. I have a question. Why isn't your image being projected on the screen? Someone help. Whoever's the IT guy here.
It's okay.
Someone has to project him onto the screen.
It's okay.
No, it's not okay. I was being projected for the entirety of the question and answer
It's okay.
session.
He just loved me too much.
Please. Who's the IT guy here?
Okay. All right. All right. So I'm too tired. I was running with a moving car, so I'm going to sit down. Allow me to sit down. I was running with a moving car. I'm so tired. Okay, so let me tell you the story. Let me go back. When Suborno was 1.5 years old, right? His mom took charge of teaching Suborno math, just like my elder son. My elder son was also very talented. He goes to Brown University to study graduate level physics. Now hear me out. Suborno's mom was teaching him 1 plus 1. Suborno, can you please tell me what is 1 plus 1 is? His mom asked him when he was 1.5 years old. Now can you tell me what is 1 plus 1, guys? Very good. Very good. Round of applause for him. kids are usually more enthusiastic than adults. As we become adults from kid, we lose enthusiasm. Please don't. Okay. So, Suborno said 1 plus 1 is 2. But hear me out. Suborno challenged his mom. Mom, if 1 plus 1 is 2, what is n plus n? His mom reaction was, what is this dude talking about? 1.5-year-old little dude is challenging me? And she did not know what to say. So she reported me. I was a security guard. Do you understand Bangla? Do you understand Bengali? আমি তখন রাতে দারওয়ানি করতুম আর দিনে Should I tell you the story in Bangla? Okay. So, okay, all right. Okay. আমি রাতে দারওয়ানি করতুম আর দিনে আমি বিএসসি করতাম ম্যাথামেটিক্সে লিমন কলেজে। তো তার মা আমাকে বললে, দেখো কি অবস্থা, এই ছেলে এই পুসকে আমাকে চ্যালেঞ্জ করে। আমি বলি 1 plus 1, সে বলে হোয়াট ইজ n plus n। ছেলের সাহস কত! তো আমি বললাম হয়তো খিদে লেগেছিল, হয়তো সামথিং হি ওয়াজ ট্রাইং টু ক্যাচ অ্যাটেনশন। তো আমি একদিন কি করলাম, এটা মুখ ফসকে এই স্টোরিটা আমার প্রফেসরের সাথে শেয়ার করলাম। তো আমার প্রফেসর আমাকে বললে, ছোট বাচ্চা, সে 2 বছর 3 বছর 4 বছর, সে কিন্তু ম্যাথামেটিক্সের অ্যাবস্ট্রাকশন করতে পারার কথা নয়, তুমি বাচ্চাটাকে নিয়ে আসো। তো আমি বাচ্চাটাকে নিয়ে আসলাম। তখন আমি কি করতাম, আমার ইচ্ছে ছিল, আমি সুবর্ণ তো সেই গল্প শেয়ার করেছে, আমার ইচ্ছে ছিল আমি ল স্কুলে যাব। আমি পলিটিক্যাল সায়েন্সে ব্যাচেলর করে ব্রুকলিন কলেজ থেকে পলিটিক্যাল সায়েন্সে মাস্টার্স করেছিলাম। তখন যখন দেখতে পেলাম সুবর্ণ ম্যাথে তার ইন্টারেস্ট বেশি, তখন আমি আমার ইচ্ছে চেঞ্জ করে ফেললাম। আমি ওকে, সো লেটস সুইচ দ্য গিয়ার টু ইংলিশ। ওকে, অলরাইট, ওকে,
Language barrier.
so where was I? So his mom informed me that Suborno started challenging him, right? So I wanted to help Suborno then. But the problem was I was not good in math. I was pursuing my degree in political science. So I changed my mind. I thought I should study math. I enrolled myself in math, in BSc in math. I enrolled myself in BSc in math. I gave up my dream to go to law school, right? But I found myself in a hot water. When I took calculus, I failed. I took it again, I failed. I took it again, I failed. How many times I failed calculus, Suborno said, you remember? 5 times. My intention was not to earn a BSc degree in math. Why did I enroll myself in math? So I can help Suborno, because he was showing his interest. 1.5-year-old, he was showing interest in mathematics. That's why I gave up my dream and I changed my career plan from law school to BSc in math. So somehow I survived. And later Suborno showed his interest in physics. So what did I do? I enrolled myself in physics. It was most difficult thing for me to pass thermodynamics. I was crying day and night. But I was happy. I was able to serve the need of who? Suborno, because he was showing interest in physics. But at 5-year-old, Suborno started challenging me in a way that I was unable to help him with my math and physics degree. So what did I do? I found another way to help him, and that is to become his cab driver. How did I do that? He would be taking classes at all the big universities in New York, and I would be taking him from one college to the other college. For example, last semester he took a class at Stony Brook High School, Stony Brook University, which is 50 miles away from New York University. So I take him from my home 50 miles to Stony Brook, and from Stony Brook to New York University 60 miles, and from New York University to Brooklyn College 30 miles, and from Brooklyn College to my home another 20 miles. Even cab driver don't drive that many miles a day. But that's what I have been doing. So why am I sharing this story to you? There are many ways you can support your children. If your children is good in math, you don't have to be good in math. You can support him or her many different ways, right? You can be their cab driver. You can be their cameraman. It doesn't matter. Just show them you are crazy for them. That's it. The moment they see your eyes that you are crazy for them, forget about it. They will do everything you tell them to make you happy. You know, when I feel like tired, less motivated, I go to the hospital Suborno was born, or my elder son Apurva was born. I go there, I take a cup of coffee, and I sit down in front of the hospital Suborno was born, and drink that tea or coffee. And my mom would, my wife, his mom would be calling me, where are you? Why you are so late? I would be telling her that I'm sitting in front of the hospital. Suborno was born. I'm like, you know, having a hard time holding my tears. That's what the source of your fun should come from. That's what the source of your fun come from. Not something else. When your children see that as a parent, I'm sharing this story so that they would do everything for you. Okay, now let's change the gear. Sometimes we often say that it takes a village to raise a child. It doesn't take a village. It doesn't even take a country. It takes whole world to raise a child. Why am I saying that? Suborno is Suborno because of, not because of, because of America, but also because of India. When Suborno was 7-year-old, the University of Pune Chancellor, Dr. Nitin Karmalkar, invited him. We got a letter from Nitin Karmalkar, University of Pune. We had no idea what University of Pune is. We Googled it. And that surprised us. University of Pune is like top 10 university in India. That was like awesome moment for us. We couldn't believe it. And we emailed just to verify that it was from him. And when Dr. Nitin Karmalkar put Suborno in front of graduate student, 7-year-old in front of graduate student, teaching them physics, only India can do it. No other country in the world would do that. Tomorrow is Independence Day. This is a good moment to take a pride of the country you were born. You should be so proud of. You should be so lucky. You could have born in any other country, but thank God you born in India. Best country in Asia. That's not it. When Suborno was 7-year-old, Kailash Satyarthi. Anybody? Can anyone tell me who Kailash Satyarthi is? Oh, he came here. Kailash Satyarthi came here. Round of applause. Wow. And Kailash Satyarthi ji nominate him to be the Global Child Prodigy Award. He gave him Global Child Prodigy Award in Delhi. Only India can do that. Ruya College put him in front of graduate student to teach physics. 2019, long time ago, when he was 7. And that never stopped. From Ruya College to Calcutta University, Asia's oldest university, to IIT. Only India can do that. If India can do it for Suborno, who was born in the United States, India will do more than that for you, because you were born in India. You're so lucky that you were born in India. To show our gratitude, let's hand over the microphone to Suborno so we can say, we can, he can sing the national anthem to celebrate Indian Independence Day.
Good thing none of you laughed or like told him or anything. That would be good. That would have been bad. Okay. 2 microphones should be enough. Oh, this one's off or on? Jana Gana Mana Adhinayak Jaya He Bharat Bhagya Vidata Punjab Sindh Gujarat Maratha Dravida Utkala Manga India Himachala Yamuna Ganga Uchala Jaladi Taranga Tavo Shubhe Name Jage Tavo Shubha Ashish Mage Gahe Tobo Jaya Gata Jana Gana Mangala Dayak Jaya He Vavat Vagya Vidata Jaya He Jaya He Jaya He Jaya 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 He